Hello and welcome to today's lecture on guided transmission media. On completion of this lecture, the students will be able to classify various transmission media. They will be able to distinguish between guided and unguided media. We will be able to explain the characteristics of the popular guided transmission media, such as twisted pair, coaxial cable and optical fiber. And here is the outline of the lecture. I shall give a brief introduction. In that brief introduction, I shall try to explain the need for studying the guided transmission media. Then we shall discuss about the transmission media classes. We shall consider different classes of transmission media. And we shall study in details the characteristics and applications of twisted pair cable, coaxial cable and optical fiber cable. These are the three guided transmission media which will be studied in this lecture. First, let us look back. As you know, the transmission media or communication media actually between the transmitter and receiver, this provides the physical path. So here you have got the transmitter, and here you have got the receiver, and in between you have got the transmission media. And the entire thing, this part is the complete data, the communication system. So communication media is very important for communication between source and destination. And in the earlier lecture, one of the earlier lectures, we have seen the Shannon-Hartley theorem that provides the channel capacity limit based on bandwidth. Here, this parameter B, which is the bandwidth of the medium, and M is the number of labels with which you are encoding the signal. So you see the capacity of the channel or the information rate at which data can be communicated depends on the bandwidth of the channel. So bandwidth of the channel plays a very important role. Similarly, if we look at another important equation that gives the Shannon limit, that provides a channel capacity based on the signal to noise ratio. So here we see this gives the upper limit for information exchange is given by B log 2 log base 2 1 plus S by N. So signal ratio plays a very important role. So signal ratio of the medium has to be studied, and we have to understand what are the different media characteristics with respect to signal to noise ratio. So this gives us the need for studying transmission media, and particularly it is very important to study the characteristics of the popular transmission media, which we shall do in this lecture. First, let us look at the classification. The transmission media can be broadly classified into two types. In the first case, we call it guided transmission media, where waves are guided along a solid medium, and such as copper twisted pair, copper coaxial cable or optical fiber. So we have got three examples for the guided media. One is copper twisted pair, second one is copper coaxial cable, third one is optical fiber. So far as the unguided media is concerned, it provides a means for transmitting electromagnetic signals through air, but do not guide them. So in such a case, we are communicating through air, and obviously whenever we communicate through air, then we have to choose proper antenna and so on, as we shall see. And this unguided transmission is called wireless transmission. And as you can see here, the various classifications, as I have already explained, there are two basic categories. One is guided, another is unguided. Under the guided, which we may call WAD, we have got twisted pair cable, coaxial cable and optical fiber, as I mentioned, and on the other hand, in case of unguided wireless communication, it is air, but it may not be necessarily air. It can be water, it can be free space, but primarily we shall be concerned with air because most of our data communication will take place through air. Now, let us look at the quality of transmission. As you send signal through a transmission media, the quality of signal will be dependent on some parameters. So, what are the parameters on which the quality of transmission will depend? Let us see how it depends on in case of guided media. So, characteristics and quality of data transmission are determined by medium and signal characteristics. Now, let us consider guided media. In case of guided media, the medium is more important in determining the limitations of transmission. That means the quality of transmission will be primarily determined by the transmission media, as we shall see. As we have already seen, the bandwidth of the medium is and the signal to noise ratio. So, and also the attenuation characteristics of the medium. So, these parameters will be very important in case of guided media. On the other hand, in case of unguided media, the bandwidth of the signal produced by the transmitting antenna is more important than the medium. So, when we transmit by using unguided media, then the frequency spectrum that is transmitted by the antenna will play a more important role than the medium itself. In other words, we can use same medium to transmit signals of different frequencies using antennas of different shapes and sizes, as we shall see. So, in that case, antenna will play the key role in deciding the transmission characteristics. So, these are the two broad situations. Now, let us focus on the guided media. First, we shall consider the twisted pair cable. A twisted pair cable consists of two insulated copper wires arranged in a regular spiral pattern. As you see in this diagram, this is one conductor, this is another conductor. You have two conductors. So, you have got two conductors and you have got, so this is insulated, here is your insulator. Insulator is there, and then there is a plastic cover in which both the cables are put in the twisted form. As you can see, there is some kind of helical form in which the wires are twisted. Now, typically you are not using just one pair of wire. Typically, a number of pairs are bundled together into a cable by wrapping them in a top protective sheath. In this diagram, as you can see, we have got several twisted pairs. Here, this is one twisted pair, this is another twisted pair, this is another twisted pair. So, a large number of twisted pairs are wrapped in a with the help of a top protective sheath, and that is actually used for data communication. So, from one building to another building, from one place to another place, such a cable with a large number of twisted pair of cables in a single protective sheath is used. That will create some problem, as we shall see later. Now, you may be asking, what is the need for twisting? Why we are twisting the wires? Why not just put two wires as it is? What is the need for twisting? Need for twisting arises because of a phenomenon called crosstalk. As we have seen in the previous slide, we are taking not just one twisted pair, but a large number of twisted pair together. So, signal passing in one pair of wire will induce signal in another pair of wire. So, in our from our experience of telephone system, we know that whenever we are talking in the background, if you listen carefully, you can hear some background background some conversation. That conversation we normally call crosstalk. The crosstalk is arising because the adjacent pairs are inducing some signal in the twisted pair of wire through which the conversation you or I am doing, or both of us doing together. Now, how it reduces the crosstalk? Actually, as you can see here, you have got this is one wire and this is another wire. So, if it is done this way, so current is flowing in one direction in one wire and it is flowing in the reverse direction in another wire. And if they are twisted together, actually the field induced by this wire will be just opposite to the field induced by the other wire. That means they will cancel out each other. Similarly, if there is a adjacent pair here which is actually acting as some kind of transmitter, then it will induce on this part, it will also induce on this part, and since they will ultimately since they are in opposite directions, they will cancel out. So what is happening in this case, the twisting is actually cancelling out the interferences between adjacent pairs of wires. So in other words, it is minimizing crosstalk. Now you may be asking the number of twists per inch, does it play any role? That means number of twists per some length, say per inch or per feet, whatever it may be, does it play an important role? Yes, actually tighter twisting provides much better performance, but also it increases the cost. For example, here we can see category 1, normally we have got several categories of twisted pair of wire. Here we see Cat 1, Cat 2, Cat 3, Cat 4, Cat 5. These are essentially categories of wires. Cat 1 cable is has got very low bandwidth, and you can send data at the rate of about 100 kilobits per second. It is commonly used for analog transmission and primarily used in telephone systems, telephone networks. Cat 2 cable has got lower bandwidth, less than 2 megahertz, and you can use data rate up to 2 megabits per second. It can be used for analog transmission as well as for low bandwidth digital signal transmission. For example, in telephone lines, T1 lines, it is used. Later on we shall discuss about these T1 lines in more details. Then Cat 3, which has a bandwidth of 16 megahertz, that allows data rates of 10 megabits per second, and this can be used not only for analog data communication, but it is commonly used for digital data communication. Particularly it is used in local area networks, as we shall see later. Category 5 has got 20 megahertz bandwidth with data rate of 20 megabits per second. It is also primarily used in digital data transmission, digital signal transmission, and commonly used in local area networks. Then you have got category 5 having bandwidth of 100 megahertz with data rate of here actually there will be 100 megabits per second, 100 megabits per second, and it also uses digital data transmission, particularly in local area networks. Although there are category 6 and category 7 are also available nowadays, but I have not given it here, just have given Cat 1 to Cat 5. And the two commonly used categories are Cat 3 and Cat 5. As you can see, as you have already seen, category 3 allows data has a bandwidth of 16 megahertz, and it is commonly used for data transmission at the rate of 10 megabits per second. And category 5 has got bandwidth of 100 megahertz, so you can use it for 100 megabits per second. And obviously, the key difference between the two is the number of twists in the cable per unit distance. As you can see, in case of category 3, the number of twists per feet is 3 to 4. So that means 3 to 4 twists per feet. On the other hand, for category 5, it is 3 to 4 twists per inch. So you can say the number of twists in category 5 is about 12 times that of category 3, because it is per feet, here it is per inch. And so we see that by increasing the number of twists, we are able to improve the performance. That's why whenever lightning occurs, or whenever there is some sparking, or a car is moving close by, then that signal is induced in this unshielded twisted pair of wire. However, this can be reduced by using shielded twisted pair, where, as you can see, we have got an additional conductor in the form of braided mesh. Braided mesh form. It is not a solid conductor, it is available in the form of braided mesh, and this metal shield can be connected to the ground, and after that there is a plastic cover. That means if this particular shield is connected to ground, then this particular metal shield will protect both the wires from electromagnetic interference. So whenever we want lesser electromagnetic interference, we should use shielded twisted pair. However, shielded twisted pair is definitely costlier than the unshielded twisted pair. So shielded twisted pairs are not that popular in our day-to-day common applications in telephone systems, telephone networks, as well as in local area networks. Usually UTP, or unshielded twisted pair of cables, are used. Here is the attenuation characteristics of different types of UTP cables. Here you see the conductor, that inner conductor that is used. We have seen there is an inner conductor, and on which then there is an insulator. This inner conductor diameter is specified here: 18 gauge, 22 gauge, 24 gauge, and 26 gauge. And here the diameters are given in inches. 18 gauge corresponds to 0.0403 inch. On the other hand, 26 gauge has diameter 0.0159 gauge. So it is quite obvious that more the diameter, higher the diameter of the conductor, lesser will be the attenuation. So 18 gauge wire gives you lesser attenuation compared to 26 gauge, and obviously the 18 gauge wire will be costlier than 26 gauge. So these are the common wire diameters and the gauge of wire given here, and this, as you can see, attenuation is given in dB per meter, and here is the frequency. So at higher frequencies the attenuation increases for UTP. So apart from increase in attenuation at higher frequencies, as the length of the wire increases, the attenuation also increases. It has been found that the attenuation is proportional to 1 by distance square. So as the distance, attenuation is proportional to distance square. So as distance increases, the attenuation becomes more, and in such a situation, as you know, we can use repeater to regenerate the signal, amplify the signal, and regenerate it and resend it if necessary. As you know, the twisted pair UTP is the simplest and possibly the cheapest the guided media used in many applications. One is the most common application is local loop in telephone lines. That means in a telephone network, the connection that you are getting to your home from the local exchange, the wire that is used is your UTP. And it is also used in digital subscriber line, DSL. Nowadays DSL is becoming more popular. We shall discuss about it in more detail. In DSL also the UTP is used. Then as we shall see later on, as we shall discuss the local area networks, there also the twisted pair of wire is used. UTP, that category 5 or category 6 cables are used in different situations for point-to-point communication, particularly 10 base T and 100 base T Ethernet network. Later on we shall discuss about it in more details. And normally the connector used is RJ45 with 8 lines. This is the type of cable connector that is used in the context of UTP cables. Now we come to the second type of guided media, that is your coaxial cable. Coaxial cable consists of a hollow outer cylinder. As you can see, there is a hollow outer cylinder. You can see this is the hollow outer cylinder that surrounds a single inner conductor. And inner conductor, this is the inner conductor, is held in place by either regularly spaced insulating rings. So here you have got solid dielectric material inside. So this is the cross sectional view of the coaxial cable, and here as you can see, this is the inner conductor, then you have got the insulator, and there you have got the outer conductor, then there is a outer protective sheath. So that forms the total form of coaxial cable. And there is a outer jacket made of plastic that is used to cover that outer conductor. So you have got two conductors, and one is insulator and a protective sheath. And so here you can see a real coaxial cable. So here is the inner conductor which is solid, and here is the insulator, then the outer conductor, and here is the protective sheath. So these are the four components: outer protective sheath, outer conductor, inner insulator, and the inner conductor. And because of this shielding, coaxial cables are much less susceptible to interference or crosstalk than twisted pair. So what possibly can be done? The outer conductor can be grounded, and then as the outer conductor is grounded, the inner conductor is shielded from interferences and disturbances, and that helps to reduce the crosstalk. And the crosstalk in case of twisted coaxial cable is much less than twisted pair of wire. And normally the BNC connectors are used in connection with coaxial cables. So here is the coaxial cable, and here is the connector. Then this is the BNC T connector, and other side can be connected to another cable. This is how the connection is done. Here is the performance of the coaxial cable. Here as you can see, on this side you have got the attenuation, decibel dB in kilometer. Here it is in kilometer. Here is the frequency F in kilohertz. So here you see the frequency range is from 0.01 kilohertz to 100 kilohertz. And here you have got three different types of cables with inner, and these two are representing diameter of the inner conductor and diameter of the outer conductor. So obviously here the diameter is less, 0.07 millimeter, and outer conductor diameter is 2.9 millimeter. In this case it is 1.2 inner conductor diameter and 4.4 millimeter outer conductor diameter, and the other one is 2.6 millimeter diameter of the inner conductor, and here is the 9.5 millimeter is the diameter of the outer conductor, and obviously this will have lesser attenuation than the other two. And the frequency range in case of coaxial cable, as we shall see, the twisted pair of wire gives you lesser, provides you higher bandwidth than the twisted pair of cable. And this coaxial cable is used in a variety of applications, in television distribution, for cable TV applications. The television signal that is coming to your house is from cable TV uses coaxial cable, and as you know, a number of channels are coming through the same cables. That means bandwidth is high. That's why it is possible to send several channels by using frequency division multiplexing, as we shall discuss later, with the help of coaxial cable. So you can transmit several frequency bands using the coaxial cable because of higher bandwidth. And it is also used for long distance telephone transmission, and because of higher bandwidth, it is possible to send 10,000 voice channels per cable. In a single cable, you can send 10,000 voice channels simultaneously, and that is possible because of higher bandwidth. It is also used in local area network. As we can see here, three categories of coaxial cables are given here: RG59, RG58 and RG11, with characteristic impedance of 75 ohm, 50 ohm and 50 ohm. This RG59 is commonly used in cable TV, which is very popular and is of low cost. Then RG58 with the characteristic impedance of 50 ohms. That means the cables are to be transmitted, are to be terminated by 50 ohms resistance, and that is used in thin Ethernet, which gives data rate of 10 megabits per second. RG11, which is thick Ethernet with characteristic impedance 50 ohms, that is also used in thick Ethernet. So RG11, RG58 and RG15, these are the three popular coaxial cables commonly used in three different applications. Later on, when we shall discuss the local area networks, particularly the Ethernet, we shall discuss about the thin Ethernet and thick Ethernet and use of two different types of coaxial cable in Ethernet technology. Coming to the third guided media, that is your optical fiber. An optical fiber is a thin, flexible medium capable of conducting an optical ray. It is made of ultra pure fused silica, glass fiber or even plastic, and it has a cylindrical shape and consists of three concentric sections: the core, the cladding and the jacket. Let us see the structure of a optical fiber cable. Here, as you can see, it has got three different parts: the core part, and there is a cladding part, and there is a jacket. And the core consists of very thin strands of fibers made of glass or plastic. This particular part is made of glass or plastic. The cladding part is also made of glass or plastic, but these two materials, the inner that core material and the cladding material, they have different optical properties that we shall discuss in detail. And so although they are made of the same material, plastic or silica, but their properties, the optical properties will be different. They will have different refractive indices, as we shall see later on. And then the jacket surrounds one or a bundle of cladded fibers. So you can have either this kind of a single optical fiber cable or a large number of optical fiber cable and bundle them together and with the help of a plastic sheet and take from one place to another. Usually 4 or 6 or 8 or 16 optical fiber cable, 16 pairs of cable. Normally it is used in pairs and for data transmission in both directions, and 4, 8 or 16 pairs of cables are bundled together and taken from one place to another. Question naturally arises, how optical fiber works? The optical fiber works, the operation of optical fiber is explained with the help of this diagram. As you can see here, to explain the operation of optical fiber, let us consider two materials. This one is of higher density than the upper one. So the density of the lower material is more than the density of the upper material. That means this can be, let's assume this is water and this is air. Then this has got higher density than the upper layer. Now here what is happening, the angle of incidence of this ray is less than the critical angle. Then what is happening, the signal is going from here and it is getting refracted because of these two materials, as you know, has got two different refractive indices. However, as the angle of incidence increases, this I value increases gradually, then that angle of refraction, this is your angle of refraction, this angle of refraction becomes 90 degree. Whenever it becomes 90 degree, we call it critical angle of refraction. Now if the angle of incidence is more, then what happens? Then it suddenly switches from refraction to reflection. As you can see here, then this light is getting reflected instead of getting refracted there. So when the angle of incidence is more than the critical angle, then this refraction occurs. Let us see how it really happens with the help of animation. As you can see here, in this case, the angle of incidence is increasing and we have reached the critical angle. Then this is the refracted ray and this is the incident ray. Now if we increase the angle of incidence further, then as you can see, now the signal, it is refracted, and now this angle of incidence is same as the angle of reflection. So angle of incidence and angle of reflection is same. So as we increased it, let us see once again. So as it is increasing, this is also increasing, this angle is also increasing, and however as it becomes more than the critical angle, then it is getting reflected rather than refracted. So here the signal is getting reflected. Now the optical fiber, we have seen how light is reflected in a optical fiber. Actually here I have shown two mediums. Actually this inner material will be the core material and outer material will be the cladding material. That will form the two materials, and then the total internal reflection will take place and the light will be passing using total internal reflection, as we shall see. Now based on the optical signal communication through optical fiber, it can be classified into three different types. One is known as step index. Actually there are two broad categories, multi-mode and single mode. Why it is called multi-mode we shall see later. And then multi-mode has got two different varieties, step index and graded index. And then you have got single mode. Let us see the three different types of optical fibers. First of all, This multimode refers to the variety of angles that we will reflect. That means in case of multimode fiber, multiple propagation path exists. That means single element spread out in time and hence limits the data rate. What is happening in this case, as we shall see, multiple signals, multiple rays will pass through, will be reflected with different angles, and as a result the length of the path will be different for different rays, and as a consequence they will reach the destination at different times, and that will lead to distortion, and it will, that's why we are calling it, it will spread out in time and it will limit the data rate. So that problem is overcome by using single mode, particularly whenever the diameter of the core is radius. Core radius is, this is a, here is a mistake, this is actually core radius is reduced, fewer angles will reflect. By reducing the radius of the core to the order of a wavelength, that means say 7 nanometer, 10 nanometer, then only one, we may assume that only one ray is passing from source to destination. So in such a case, only a single angle or mode passes through the optical fiber, and that is called, that's why it is called monomode or single mode. Then as I mentioned, there are two types in case of multimode: multimode graded index and multimode step index. Now in case of multiple step index, as we shall see, the core and cladding has got two distinct refractive indices. On the other hand, in case of multimode graded index, the refractive index of the material varies gradually from the center to the outer edge. Let us see with the help of a diagram. Here you have got the monomode type of step index fiber. Here, as you can see, diameter is very small, 8 to 10 micron of the core, and this is the cladding, and as you can see here, the refractive index of this core material is N1 and refractive index of the cladding material is N2, and diameter of the core is 8 to 12 micron, diameter of the cladding is 125 micron. On the other hand, here you have got your multimode step index fiber. Here the diameter of the core material varies from 50 to 200 micron, and diameter of the cladding can vary from 125 to 400 micron. And the refractive index in this particular case for the core is N1 and the cladding is N2. Now for the third variety, that is your multimode graded index fiber, as you can see, the core refractive index is gradually changing. In the center it is 0, then it is gradually changing. As you can see, this is the refractive index. It is gradually changing from N1 to N2 here, and here it is N1, here it is N2. So as you go from here to here, it is gradually changing from N1 to N2, and this will lead to different characteristics. Let us see with the help of a animation how it works. This is the case in case of step index fiber. As you can see, light is going through total internal reflection and it is going to the other end. Now there can be another ray with a different angle of incidence, and as you can see, the number of reflections that it suffers is different, and as a result, if you measure the path length of these two rays, this ray and this ray, then they will be different, they cannot be same, and as a consequence this leads to spread out. And this is the case of multimode graded index fiber. In the previous case, as you have seen, there is a abrupt reflection, and as this leads to some kind of distortion. This can be minimized in multimode graded index fiber, and here as the refractive index gradually changes from center to the interface between the cladding and core, the light will be gradually bending, as you can see here. So you can see there is no sharp bending, light is gradually bending and going it in this manner. However, this can, although the bending is occurring gradually, but you can have different angle of incidence, and as a result multiple rays are passing from source to destination, from one end to the other end. On the other hand, this is the case for monomode step index fiber. As you can see in this particular case, as if a single ray is going, axial ray is going from source to destination. So there the question of multiple ray does not exist in case of single mode fiber. What are the consequences? The consequences of this is the single mode fiber will have much less distortion. That means signal will not spread. You know, normally we call it measurement of the eye. That eye will be quite open in case of single mode fiber compared to multi-mode fiber, and the spacing between the repeaters will be much longer in case of single mode compared to multi-mode. That means in case of multi-mode fiber, the repeater spacings will be more closer than single mode fiber. So here some of the different optical fiber types. Here it is designated by the core diameter by cladding diameter. So here is the core diameter 50 micron, cladding diameter 125 micron. So this is multi-mode graded index. Here is another example, 62.5 by 125, that meaning that 62.5 stands for core diameter, 125 micron is the cladding diameter. It is also multi-mode graded index fiber. And then you have got 100 by 125. Here the core diameter is 100 micron, cladding diameter is 125 micron. This is also multi-mode graded index. And then 7 by 125. Here we see the diameter is only 7 micron in case of single mode fiber or monomode fiber. And cladding diameter, as you can see, same for all the 4 cases. Now an important parameter is the numerical aperture. Numerical aperture actually relates to the difference between the refractive indices of the core and cladding. So N1 is the refractive index of the core, N2 was the refractive index of the cladding. So this numerical aperture is square root of N1 square minus N2 square, or you can write it as N1 square root 2 delta, where delta is the core cladding index difference. That means N2 is equal to N1 into 1 minus delta. So that means the core will have higher refractive index than the cladding, and the delta has the typical value of 0.01, and as you know, we can use the material either plastic or silica. If we use silica, then N1 is equal to 1.48. Now with this parameter in mind, if we consider N1 and N2, the refractive indices of 2 mediums, can you find and here there is a problem, find out the critical angle for the above situation. That means situation is where you have got 2 core cladding materials with difference in refractive index of delta, that is 0.01. So you can find out the critical angle, and this is given as a problem to you. Now what are the sources of light in case of optical fiber? Usually there are 2 sources. One is light emitting diode. Light emitting diodes are very low cost, as you know. It is used in almost all equipment for display purposes. That can be used as the source of light. It is very cheap. It has got greater temperature range. It can withstand greater temperature range. It has longer life because it is semiconductor material. And however, because the power coupled is very small, for example, in case of 50 micron optical core diameter, the power that can be coupled is only 25 microwatt. As a result, it can be used for only short distance communication, and particularly it is used in multimode fiber. On the other hand, there is another alternative source of light, that is injection laser diode, which is costlier. However, it is much more efficient than the light emitting diodes, and it allows longer distance because it can couple much higher power, about 1 milliwatt in case of monomode fiber. That means in case of monomode fiber, commonly that injection laser diode is used. For multimode fiber, commonly light emitting diode is used. On the other hand, on the other end, at one end you will be using some light source, at the other end you have to receive the signal, detect the signal, light signal. The detection of light is done with the help of two different types of photodetectors or photodiodes. One is pin photodiode or pin photodetector, another is avalanche photodiode or APD. Obviously, the APD has better characteristics, better signal to noise ratio than the pin photodetector. However, the avalanche photodetector is costlier than the pin photodetector. Normally, pin photodetector can be used with multimode fiber where the source of light is LED and where low cost is the primary criteria. On the other hand, in case of single mode fiber, the laser source is used, injection laser diode is used as the source of light, and avalanche photodiode is used as the detector. Here is the attenuation characteristic of optical fiber. As you can see here, the loss is dB per kilometer. Here it goes down to 1 dB per kilometer. So attenuation is very low, and particularly it is used in three normal ranges. One is 850 nanometer band, 1300 nanometer and 1500 nanometer. So these three range is used here. As you can see, 1500 nanometer, here is your 1300 nanometer and 850 nanometer. These are the three frequency spectrum ranges where it is commonly used. What are the advantages of optical fiber? Optical fiber provides you higher bandwidth, leading to greater capacity. As you know, you can pass 2 gigabits per second over tens of kilometers. It is used in long haul fiber transmission, and it is becoming increasingly popular in telephone network. Nowadays, most of the telephone networks are using this optical fiber communication. So you can send about 900 miles with 20,000 to 60,000 voice channels because of very high bandwidth of optical fiber. And the material that is used is silica or plastic. It is very cheap, small in size, very lighter in weight because it is not a metal, so weight is very less. And as I mentioned, it has got very low attenuation. However, moreover, another important property is it has got resistance to corrosive material. You know, the metals gets corroded, oxidation occurs when it comes in contact with say moisture and temperature. That kind of corrosion does not occur in case of optical fiber material. And another important property is it is immune to electromagnetic interference. So it is immune to electromagnetic interference. That means it is very suitable for outdoor applications, outdoor cabling. All the outdoor cabling in local area network is commonly done by using optical fiber. And it has got much greater repeater spacing compared to either twisted pair or coaxial cable. The cost of the three different guided media we have considered can be compared in terms of cost, bandwidth, attenuation, susceptibility to external noise, and security. So as you can see here, the UTP, unshielded twisted pair, has lowest cost, bandwidth is much lower, attenuation is much higher, electromagnetic interference is higher, and also security wise it is very low. You can do tapping very easily, eavesdropping can be done very easily. On the other hand, coaxial cable has got moderate cost with bandwidth of 350 megahertz and gives you data rate of 500 megabits per second. It has got moderate attenuation and electromagnetic interference is moderate. Security is low as same as more or less same as your UTP. On the other hand, optical fiber has got little higher cost, very high bandwidth, 2 gigahertz. You can have data rate of 2 gigabits per second. Attenuation is low, you can have repeater spacing of 10 to 100 kilometer, and EMI interference is low because electromagnetic interference cannot take place with light, and it has got higher security. It is very difficult to get data from optical fiber. So here if you look at compare the attenuation characteristic, as you can see, attenuation is much low for optical fiber compared to twisted pair and coaxial cable. Main difference between twisted pair and optical fiber coaxial cable is that coaxial cable has got higher bandwidth compared to twisted pair. Here are the review questions. On what parameters the quality of transmission depends in case of guided transmission media? First question. Second question is why wires are twisted in case of twisted pair of transmission medium? Third question is give a popular example where coaxial cables are used for broadband signaling. Fourth question is find out the critical angle for a step indexed optical fiber for N1 is equal to 1.04 and delta is equal to 0.04. In what way multimode and single mode fibers differ? So these are the 5 questions to be answered in the next lecture. So here are the questions that I gave in the previous lecture. Let us look at the first question. Answer is attenuation. Attenuation will be equal to 10 log 10 1 by 50. So this will be equal to minus 16.9 dB. Question 2 was assuming there is no noise in a medium, bandwidth of bandwidth 4 kilohertz, determine channel capacity for encoding level 4. As you know the equation, the C is equal to B log 2 M. Here it is log 2 4. This gives us 16 kilobits per second. So this is the channel capacity that is possible in this case. Third problem was a channel has a bandwidth of 10 megahertz. Determine the channel capacity for signal to noise ratio 60 dB. So as we know the formula, C is equal to B log 2 1 plus S by N. So with the help of this you can find out. So 10 log 2 1 plus 60, this gives you 59.307. Here it is megahertz, so megabits per second. So this is the maximum possible channel limit, you can say, 59 megabits per second. Fourth question was the digital signal is to be designed to permit 56 kilobits per second for a bandwidth of 4 kilohertz. Determine the number of levels and signal to noise ratio. So this can be calculated by using 2 different formulas. In the first case, you have to use this formula, I is equal to 2 into M log 2 M. So here M is equal to, you have to find out the M. and I is given already 56. So 56 is equal to 2 into 4000 into log 2 m. From this you will get m is equal to 2 to the power 7, actually 56 kilobits, so you have to have zeros, 56,000 zeros. 7 is equal to 128 levels. Similarly, you can find out the signal to noise ratio from this equation. That means signal to noise ratio will be found out from this formula. C is equal to B log 2 1 plus Sn. So here C is given, B is given, a signal to noise ratio has to be found out. C is equal to 56,000 is equal to bandwidth is 4000 log 2 1 plus signal to noise ratio has to be found out. From this you can find out S by N is equal to about 43 dB. So here we have given the answers of all the questions that was given in the last lecture. Thank you.